Nuclear Engineering Summer School. And I'm Professor Sarah Pozzi of the University of Michigan and the director of the MTV. Welcome, everyone. It's my pleasure to welcome today's speaker, Dr. Sonja Schmid. She's an associate professor at the Department of Science, Technology, and Society at Virginia Tech and the co-director of the STS graduate program in Northern Virginia. Her research originates at the interface of national energy policies, technological choices, and non-proliferation concerns. For her first book, which is titled Producing Power, the Pre-Chernobyl History of the Soviet Nuclear Industry, published by the MIT Press in 2015, Sonja worked in Russian archives and interviewed veterans of the Soviet nuclear power program. She also studies Soviet nuclear technology's transfer to Central and East European nations during the 20th century and beyond, to trace the fate of Soviet-designed nuclear artifacts once their host nations joined the European Union. Her most recent project focused on the challenges of globalizing nuclear emergency response and was supported by an NSF Career Award. She hosted monthly speaker series that are now available as an online archive. At Virginia Tech, she teaches courses in social studies of technology, science, and technology policy, sociocultural studies of risk, and energy policy. So it's my great pleasure to bring you Dr. Schmid, who currently serves on the U.S. Department of Energy's Nuclear Energy Advisory Committee. That's a high-level committee in D.C. Her background includes humanities degrees from University of Vienna, Austria, as well as a PhD in science and technology studies from Cornell University. And before joining Virginia Tech, she spent time as a postdoc at the Center for International Security and Cooperation at Stanford, or the CSAC Center, where she also taught in the STS program. So let's welcome Professor Schmid. The floor is yours.
Thank you, Professor Pozzi, and thank you all for joining. I have some slides I'd like to share, so let me see if I can get this going. All right, so under this fairly generic title, I would like to introduce you to a few things, and I just wanted to give you some warning. I am working off of a laptop, so I have a small screen. So if you need to tell me something important, please speak rather than put something in the chat box because I won't be able to see that. Okay, so what I would like to talk briefly about today, what is STS? What is Science and Technology Studies? And then also, how can STS collaborate with nuclear science and engineering programs? I want to talk a little bit more about my own scholarly background to show how historical and comparative analysis is key to more informed decision-making, and also what warrants my participation in this nice, exciting summer school. And then I want to focus on origins and some context of nuclear boundary work, specifically between nuclear weapons and nuclear power, and some new and old opportunities and challenges facing this field. So to start with, what is STS and why is it ideally suited to address, in my opinion, the intersection of science and technology and society, policy, and governance, particularly in the field of nuclear energy. So STS stands for either Science and Technology Studies or Science, Technology, and Society, and is a field that conducts scholarship and public engagement at the intersection of science, technology, and society. It is a growing field that draws on the full range of disciplines in the social sciences and humanities to examine ways that science and technology shape and are shaped by our society, politics, and culture. We study contemporary controversies, but also historical transformations. We study policy dilemmas and broad philosophical questions. STS is ideally suited to address the intersection of science and technology on the one hand and society, policy, and governance on the other. In the words of Cornell Professor of Science and Technology Studies, Stephen Hillgardner, STS is an academic field concerned with the study of knowledge as a social phenomenon. It considers knowledge, especially but not only scientific and technical knowledge, in all its forms, whether embodied in technologies, texts, persons, competencies, practices, etc. In particular, the field examines A, how knowledge is produced, spread, contested, contained, challenged, stabilized, displaced, destroyed, evaluated, and presented, and B, the consequences and normative dimensions of knowledge and the means of producing it. This situates STS ideally, I would argue, to collaborate with nuclear science and engineering programs. And at Virginia Tech, our STS program, together with the School of Public and International Affairs and the Nuclear Science and Engineering program, have created an interdisciplinary graduate certificate in science, technology, and policy. This certificate integrates policy and management with nuclear science and technology to prepare students from diverse educational backgrounds for careers managing and leading nuclear policy organizations across a spectrum of activity in safety, security, safeguards, and non-proliferation. The certificate courses offer fundamental knowledge of concepts in nuclear science and technology that are relevant to policy issues, and also provide an introduction to topics in safety, security, and non-proliferation, which occupy the bulk of government concerns with nuclear issues. Finally, the certificate allows students to interact with policymakers in the field through briefings, simulations, and exercises. And that little graph that you see here just symbolizes that all students are required to take 2 courses, and one is kind of an anchor course that introduces them to all kinds of nuclear topics, and then an interdisciplinary team project. And each student then elects a course from a technical area and one from a social science or policy area for a total of 4 courses. And there's more information available on our website. And we have graduated the first few students with this certificate last year. So a little bit on my background. Professor Pozzi already mentioned my book, and I'm providing this not just to advertise myself, but also to justify what qualifies me to speak in this wonderful summer school series, because it's not just my curricular initiatives, although I'm very proud of those, but also my research that I wanted to, that has focused on a few areas that are relevant to the topic of nuclear science, technology, and policy. So this book, which was apparently known to the makers of the highly successful HBO miniseries Chernobyl, although I doubt they actually read it because the series didn't quite pick up the argument it was trying to make, namely that the Chernobyl type reactor, the RBMK, was considered up to the 1986 disaster a highly successful Soviet innovation, and that its adoption and widespread construction inside the Soviet Union made the Soviet nuclear industry the behemoth it is today. The fact that its design is a direct offspring of military production reactors at the time of its introduction only added to its popularity. More than other nuclear power reactors then, the RBMK symbolizes the liminal position of nuclear energy between electricity generation and other civilian applications on the one hand, and the nuclear weapons sector on the other. I'll return to this peculiar positionality in a minute. As Professor Pozzi mentioned, I've also written on Soviet nuclear technology transfer, specifically to the USSR's former satellite states in Central and Eastern Europe. This topic still fascinates me because the Soviets, on the one hand, experimented very widely with exporting nuclear materials and expertise, but they were also highly sensitive to non-proliferation concerns. Furthermore, they built nuclear power plants whose electricity production was partially earmarked for export via high voltage transmission lines, an idea that works very well in a densely populated area such as the European continent. With the collapse of the Soviet Union and the accession of many of these Central and Eastern European states to the European Union, these Soviet-designed and Soviet-built, in many cases, nuclear reactors were shut down, supposedly for safety concerns. Many, however, kept running and have become electricity exporters in their own right. The push and pull over nuclear energy within the newly enlarged European Union is a topic I've been watching with growing interest, especially in the light of the recent German nuclear phase-out. Most recently, I've been working on a project that investigated the post-Fukushima initiatives to ramp up nuclear emergency preparedness and response, both at the national and the international level. Using a few case studies for comparative purposes, I wanted to understand how these markedly different approaches in different countries could come together at a global level, realizing that fallout from severe nuclear accidents such as Fukushima rarely stay confined to one nation state. This has also led me into legal territory, where I had a chance to work on compensation schemes in different areas of the world and how the responsibility for accidents with transboundary effects is being negotiated and written into agreements at the international level. And finally, over the past couple of years, I've been working with my graduate student, Taylor Loy, and looking specifically at the production of tritium in the United States from the perspective of the erosion of the long-standing boundary between civilian and military nuclear applications. Unbeknownst to many, tritium, which is a critical element in modern nuclear weapons, is now being produced in civilian power-generating nuclear reactors. This creates all kinds of fascinating problems, from classification to chain of custody, and from divvying up responsibilities between utilities and government agencies, and also implications of such collaboration for regulation and public oversight. So let's back up a little bit and start with some historical context. Nuclear science and technology, and eventually nuclear weapons, emerged from a wartime crash program to develop a super weapon and win World War II once and for all. The US dropped nuclear weapons on the Japanese cities of Hiroshima and Nagasaki, leveling them in one terrifying blow. Even before that, an arms race of unprecedented scale developed among former World War II allies and eventually led to 5 nuclear weapons states that are recognized by the 1970 Treaty of the Non-Proliferation of Nuclear Weapons: the US, the former Soviet Union, now Russia, Great Britain, France, and China, and 4 more since then: India, Pakistan, North Korea, and Israel. And I wanted to share with you just a little bit of this artwork by Isao Hashimoto, a Japanese artist, titled 1945 to 1998. It's a time-lapse map of every nuclear explosion since 1940, or between 1945 and 1998. I'm going to try and play a little bit of this for you. So basically, each nation gets a blip and a flashing dot on the map whenever they detonate a nuclear weapon, with a running tally kept on the top and bottom bars of the screen. And it leaves out, obviously, North Korea's nuclear tests in the years since 1998. That's a shocking visualization, as Hashimoto said, the fear and folly of nuclear weapons. And you can, check out the entire video afterwards. So almost simultaneously with the development of nuclear weapons came a turn toward peaceful nuclear applications. in part, and that was accompanied by a massive public relations initiative all around the world, suggesting that nuclear energy was, among other things, too cheap to meter. It would eventually power cars and trains, even planes. It would find applications in medicine, agriculture, in industry. And for the scientists involved in the nuclear weapons development, this didn't only come as a kind of atonement, it was also a way to turn the horror of nuclear bombs into hope and the promise of a brighter, better future. Nuclear energy and its applications in electricity generation, industry, medicine, agriculture, transportation, etc., elicited both awe and fear, touted as the pinnacle of progress. They inspired scientists, engineers, architects, planners, artists who composed songs and made movies, and writers. These are just some examples from the 1950s and 1960s when this atomic enthusiasm was at its peak. You see a car, a train, some kind of a flying module, and again, how energy dense the nuclear energy was believed to be to become too cheap to meter. And in this process, a boundary was introduced between military and civilian applications. This boundary is quite arbitrary, yet very powerful, and it is supported by materials, institutions, expertise, treaties, etc. And I would like to focus on this boundary for the rest of this talk. And what I'd like for you, esteemed listeners, to keep in mind as we go through our current opportunities and challenges, where climate change, a geopolitical order that is changing after a relatively long period of stability, and social changes are leading to a fundamental renegotiation of this very boundary. And just to think about this a little bit more, the boundary between these different kinds of nuclear applications is not only about what is it that belongs in each bucket. So what belongs, for example, in the nuclear weapons bucket, such as highly enriched uranium and plutonium, whereas you have maximum fuel burnup and steady electricity generation in the nuclear power bucket. And this isn't just limited to materials. It extends into expertise, best practices, and work routines. So for instance, we would associate secrecy more with nuclear weapons than with nuclear power, while cost effectiveness would feature more prominently at a nuclear power plant. But there are also cross-cutting issues such as reliability, safety, and perhaps nothing I need to stress to students in a monitoring and verification program, verifiable materials accounting. But there are questions about where to draw this boundary, right? This is the whole question of supporting peaceful nuclear applications without enabling nuclear weapons proliferation. For example, what are the potential consequences of recycling or reprocessing spent nuclear fuel? And it also raises the issues of thresholds and dual-use materials and technologies. If we ask the question about who draws this boundary and who maintains this boundary, we get into this whole discussion about how the currently recognized or acknowledged nuclear weapons states and the non-nuclear weapon states relate to one another and how they maintain some kind of balance between the so-called haves and have-nots. Why is this boundary being drawn and being maintained? Obviously, you would say to keep the number of nuclear weapon states low, to keep it stable, keep the world safe, and use nuclear energy instead for power generation, desalination, hydrogen production in medicine, etc. When is it important to, when was this boundary drawn? As I mentioned, it was introduced quite early, and the idea embedded in the nuclear non-proliferation regime, which basically is in itself a trade-off between, we will assist you with nuclear power if you forego the development of nuclear weapons, has been extended indefinitely. So this boundary is is envisioned to last forever, right? These are two separate spheres, no pun intended. And how do you maintain this boundary? There's obviously economic incentives, but there's also treaties such as the Non-Proliferation Treaty I already mentioned. There is institutions such as the International Atomic Energy Agency and the safeguards and inspection regimes that it supervises. And so I'd like to invite you to do two things going forward in this talk. First, think about the social, political, and even cultural consequences of seemingly narrow technical and economic choices. And second, consider how a choice or a decision in one of these two areas that you see on the screen here potentially plays out in the sector across the boundary. For example, what effect would an arms control treaty have on nuclear fuel availability? What would a renewed US domestic enrichment capability, ostensibly to supply new designed reactors with domestically sourced fuel, do for the nuclear arsenal and to disarmament initiatives? I would argue that historical and comparative analysis can serve as the key to more informed decision-making and balanced understanding. Understanding this kind of boundary work. By boundary work, which is, by the way, a term introduced by the sociologist Thomas Guerin in the 1980s, I mean here specifically separating and doing the work of separating and keeping separate the two areas of nuclear weapons and nuclear power in terms of material characteristics about the institutions involved and the actors participating, while downplaying the commonalities between the two. In a way, one could argue that the entire nuclear non-proliferation regime is built on the existence and maintenance of this boundary and the two areas it keeps separate. You promise not to acquire nuclear weapons, then we will assist you with creating or building up a civilian nuclear power program or other civilian nuclear applications. We will then monitor, inspect, and safeguard that nuclear power program to make sure you don't illicitly use it to develop nuclear weapons. And so for the rest of this talk, when we talk about different challenges and opportunities, I'd like to invite you, rather than buy into this clear-cut separation, instead hold the tension between these two sets of issues present and stay aware just how connected they are. In other words, maybe think about a nuclear energy ecosystem where everything is connected to everything else. What this idea or this image highlights is that we don't have to rely on just technical fixes to maintain a certain order, but that we have other powerful and sophisticated instruments available to us, such as treaties, I already mentioned, regulation, but also think about subsidies, think about taxes, tariffs, and many other policies. Such instruments allow us to order this nuclear ecosystem, to incentivize or de-incentivize behaviors of individuals or institutional actors, of state actors and non-state actors. Furthermore, think about the nuclear ecosystem that is also subject to opinions, values, and preferences. Those are things that are much harder to steer in any particular direction, but that nevertheless drive many an activity. So let's keep this boundary in mind when we think about new and old opportunities and challenges. When it comes to nuclear energy, we're facing a number of such opportunities and challenges, most of which are in one way or another connected to this boundary between military and civilian applications of nuclear energy. And among some of the opportunities, and I'm not claiming to be exhaustive here, I've divided them roughly into technical, economic, and political opportunities, are that, for instance, right now we have a series of new reactor designs on the table and under review, big and small, conventional and more revolutionary designs. The emphasis is on the high energy density that nuclear energy provides as opposed to other, to renewable energies, for example. And we also have new, safer technologies available at almost any stage of the processes. In terms of economic opportunities, there's nuclear power has recently been categorized as carbon friendly. We have, especially in the United States, new nuclear startups. There's government subsidies. There's hope that small modular reactors and their mass production will decrease the initial capital investment for nuclear new build, which is often and has been an obstacle in the past. And then also in terms of political opportunities, there seems to be an increasingly favorable public opinion towards nuclear energy, especially in the context of climate change. There is a strong identity and position of the IAEA, the International Atomic Energy Agency, on nuclear facilities in armed conflict and how to keep them safe. There's new disarmament initiatives, ranging from the humanitarian initiatives to the ICANN group that wants to abolish nuclear weapons, that won the Nobel Prize. So there's a bunch of new opportunities out there. What is at stake here then in terms of the boundary I mentioned? Nuclear power is being normalized yet again and presented as a mastered technology, despite real and persistent challenges. And I'll get to some of those in a minute. New designs, for example, sometimes rely on higher enrichment fuel or propose to recycle existing spent nuclear fuel, both of which have implications for enrichment and reprocessing technologies and facilities. There's also climate implications of not just nuclear power, but also nuclear weapons. If some of you maybe remember the discussions of the nuclear winter, and there's also a very long on-ramp for nuclear new build to make an actual difference in terms of climate change mitigation. There's also questions about startups, commercial startups versus state-led nuclear initiatives. That has potential implications, especially when we talk about enrichment and reprocessing technologies that have implications for the spread of nuclear know-how and the ability of states to classify certain knowledges. And again, these are just some thoughts, and I'm sure you will all have many more to contribute here. In terms of challenges, again, I'll just mention a few. The US nuclear expertise and nuclear sector is has pretty much atrophied over the past few decades. There is, for instance, no US domestic enrichment capability at the moment. Many nuclear power plants are reaching or have reached their end of life and are operating on extended lifespans. We have also seen severe accidents in areas or in countries, in industries where we really didn't expect them. The Soviet, Chernobyl has often been dismissed as an outgrowth of a bad, corrupt, you name it, system. But then, we were faced with Fukushima, and that could not as easily be dismissed as the outcome of an undisciplined and low-tech system, even though I strongly object to those charges. There's also the reverse challenge with climate change, namely extreme weather patterns for like storms and droughts that potentially can affect the safe operation of nuclear power plants. In terms of economic challenges, the nuclear industry continues to struggle with ballooning investment, capital costs, extensive delays, but also the changing idea of what a grid should look like and the grid decentralization, at least for conventional large plants, possibly not for SMRs. This presents a challenge. These big base load producers cannot be as easily decentralized as, say, a solar panel or a single windmill. Also, there are ongoing supply chain interruptions due to the public health emergency we witnessed. The pandemic made material bottlenecks clear, but also highlighted potential workforce problems. Certified, experienced operators cannot be trained up quickly to substitute for widespread illness patterns that we haven't seen before the pandemic. Construction and other labor is subject to other challenges, such as shared living quarters, where exposure is much harder to avoid or even control. And then, of course, we have political challenges. May I mention the Ukraine war, but also the expiration of landmark arms control treaties and disarmament setbacks. For instance, the US backing out of treaties, alliance commitments, suffering some strain in terms of trust and assurances. And again, challenges in the realm of civilian nuclear applications, whether that's power generation or medical isotope production, to some extent also affect the weapons sector, even when that isn't in the news as much. Nuclear weapons also have to be safely maintained. They have parts that have to be regularly checked, tested, and replaced. And they also rely on a qualified workforce to keep them safe. So holding this tension between nuclear weapons concerns and nuclear power concerns is really critical when we look at these challenges and these issues. And it's really important, I believe, to always think about the implications for the other sector when we talk about one of these sectors. This is also a disciplinary problem. There exist definitely silos of expertise. So we have the international relations scholars who only worry about weapons and diplomacy and treaties. And then we have nuclear engineers who only worry about safety and operations. And we have policymakers who are kind of trying to straddle this without any kind of, or oftentimes without much technical knowledge. So who are the people who can keep both these problems in mind, who can hold this tension? And this is also a workforce issue. Do we want to train Homer Simpsons who just push buttons, or do we need to rely on whole nuclear workers who are able, willing, and trained to analyze and understand technical issues when they are debating policy choices, who evaluate the geopolitical ramifications when developing new designs, who can identify and examine diplomatic options and trade-offs when discussing, for example, technology transfer, bilateral or multilateral contracts, or trade agreements, who can understand that any technical, economic, and political choices have consequences, and who are competent in mapping different options. And yes, I forgot to click to show you Homer Simpson, of course. So the technologies we choose always impact the way we live, and the way we choose to live affects the technical choices that are available to us. Our choice or choices of technologies and way of life are a package. We choose them together. Countries all over the world have made different choices about the future of nuclear energy. Some plan to shut down or have shut down all remaining reactors. Others energetically build new ones, and still others, including the United States, are still deliberating. And these are just the technical choices, but choices about how we want to live are always part of those technical choices. In addition to available technical solutions and what we can accomplish with those, our choices will inevitably be based on our society's preferences, how we want to live. So what we do need are engineers and scientists and policy. What we do need is engineers who are able to understand the economic and political consequences of their technical innovations. And we need international relations theorists and policymakers who understand the technical dimensions of diplomatic and policy choices. As a society, and in our case, a democratic society, we're faced with choices that come not only in the form of new designs, advanced technologies, and improved technical safety, excuse me. But that are also, the choices also come in the form of social and socio-technical choices, as we'll need to figure out what kind of social arrangements each of these technical options entail, suggest, or perhaps even require. For example, if we want to support free market entrepreneurs promoting new designs, how much control do these new designs suggest? Who will license, monitor, and manage the safety of modular reactors, especially once they're put together in assemblies of many? How will a startup company supervise and secure exports of their artifacts? These are just some of the questions I wanted to raise here. As Sheila Jasanoff, a prominent STS scholar at Harvard, put it, the ways in which we know and represent the world, both nature and society, are inseparable from the ways in which we choose to live in it. So in other words, in addition to available technical solutions, our choices will inevitably be based on our society's preferences. And with that, I'm done with my talk. Here are some useful links, again, to this interdisciplinary graduate certificate in nuclear science, technology, and policy that we're offering, and also the seminar on interdisciplinary research and education in nuclear emergency response, the SIREN online archive that you're welcome to sign up for if you so desire. Thanks again.
Excellent. Thank you so much, Professor Schmid, for your great talk. We have a few questions, so I'm going to start with a few questions here. The first one has to do with nuclear treaties that you talked about. And the question is, are all the powerhouse countries signing these treaties, or is it only the developing countries? So who is a part of these treaties?
So that depends on which treaty you're asking about. The treaty on the non-proliferation of nuclear weapons is as I mentioned, the 1970 treaty that is quite short, and most countries in the world are actually signatories to this treaty. That treaty recognized, as I mentioned, only a limited number of nuclear weapon states. So that's why this nomenclature is sometimes a little bit confusing. Under the NPT, only the 5 states that had nuclear weapons by the time the NPT was signed are recognized as nuclear weapon states. That doesn't mean that there aren't other countries that have nuclear weapons, either because they didn't sign, the NPT, or because they withdrew, as was the case for North Korea. So while they have, and the NPT does not only include the signature doesn't just say our country will not seek nuclear weapons. It also the treaty text also obliges the signatories to pursue reasonable steps toward disarmament, which was the trade-off with the have-nots, right? So the countries that signed this treaty also signed a treaty that said that the nuclear weapon states would engage in good faith efforts to actually get rid of nuclear weapons, and this hasn't happened, obviously. So that's why we that's why we see some cracks in the non-proliferation regime, because while you could say the non-nuclear weapon states, according to the NPT, have held up their end of the bargain. They have not acquired nuclear weapons, but the nuclear weapon states have not held up their end of the bargain. They have actually, modernized and increased their nuclear arsenals.
Absolutely. Thank you very much for that answer. And related to this first question, there's a question about how do we stop countries from backing out of a treaty? What are the means that we can use to prevent a country from backing out?
Again, this is I'm sure there's a legal answer, and I'm not a legal scholar. The NPT actually has a clause in it that says that a country can give notice and can say, I'm leaving this treaty. So on one level, you could argue this is a legally solid way to leave this treaty, to just exit it if that doesn't work for you anymore. But the question that I think is being asked is, how do we keep working together to make this treaty a reality, and to actually not only accomplish the one goal, right, that we don't increase the number of nuclear weapons states, or states that possess nuclear weapons, but that we actually decrease the existing nuclear weapons in the world, which was another goal articulated in this treaty. And there have been recent initiatives, as I mentioned, both the humanitarian initiative that focuses on the humanitarian consequences of nuclear weapons, and the I can't spell out the abbreviation. ICAN, the initiative, I think, for the abolishment of nuclear weapons, that was awarded the Nobel Prize recently. So there is some movement in terms of disarmament, but let's just say expanding and modernizing a state's a nuclear weapon. If a nuclear weapon state expands its nuclear arsenal, in the face of the goals laid out in the treaty, that's probably not going to lead to trust in their good faith efforts to disarm, and may not result in countries to stay in the treaty forever.
Absolutely, thank you. And the current situation between the US and Russia makes it very difficult for us to even think about arms control right now. So future arms control treaties are right now on pause, and we've seen Russia retract from START treaties. So right now it's a very challenging geopolitical environment. We have several other questions. I'm trying to pick one that will be interesting for many. Let's see here. What do you think is the biggest factor for a country to no longer consider nuclear power? So the use of reactors and nuclear power, if they previously had it. So I think this is reference to, say, Germany, who decided to stop its reactors. What do you think are some of the factors that come into play in that decision?
Well, again, it's rarely one set of factors that play into such a big decision. The German phase out, I'm still stunned that it actually happened, because for years I was watching it, not quite like a tennis match, but they made 180s a couple of times in terms of, no, we'll keep it, no, we'll phase it out, no, we'll keep it. And it was actually Fukushima who that dealt the death blow to the German nuclear industry and nuclear energy project. And it was fascinating to watch the final kind of year of German nuclear power plants operating, because that coincided with the Russian invasion of Ukraine, and the German backup plan was to use more gas, right? And that didn't happen. So all of a sudden they found themselves in this absolute critical crunch zone, where their renewable energy Energiewende was not yet up and running. they couldn't really rely on Russian gas anymore. So they reverted to burning coal, which is, in terms of climate mitigation, the absolute worst choice, right? But a nuclear phase out is not something that happens overnight, right? That's part of why I'm so fascinated with nuclear power plants to begin with, because those are technologies unlike other power plants. In other power plants, you can, turn off the engine, shut the gates, and walk away. I'm exaggerating. But in a nuclear plant, you literally are stuck with maintaining that plant in a safe state with a number of employees for a lengthy period of time. So imagine you want to phase out your nuclear industry. You need to plan that, long term. You need to set up staff that can maintain that. You need to also let go some staff, probably. You need to bring in other staff that can take care of, decommissioning, etc. So that process was, at some point, they weren't able to stop it. They delayed it for a while, given the precarious situation with the Ukraine war. But it was considered too dangerous, which is kind of ironic, given that the German nuclear power plants were probably the safest nuclear power plants operated anywhere in the world. So again, I think the what I was trying to get at in my talk is that it's not just technical or economic factors that influence such decisions. There are these intangibles, right? That I was talking about: opinions, preferences, values, that drive ultimately these decisions and that make an economic decision acceptable or not. So these, where you make these decisions is not just an engineering decision. It's a value-laden decision, and that's why the humanities and social sciences are so important to include in this, to understand, that this is a fuller picture that we need to understand. And sure, you could run a society based on technical considerations only. That's what is being done in China. That's what's being done in Russia. The Soviet Union, the country that I've studied closely for many years, was nicknamed the country of engineers. Right? It was a technocracy. It was a state that followed engineering principles, that followed the logic of engineering, right? We have a problem and here's the solution, and that's what we will do. We have projections and we build up the industrial capacity of the country to meet those projections as best as we can, and then we adjust. It was a very mechanical way of living, and the society had to kind of tag along. They were not asked. They were not being asked. In a democratic society, that's much messier, right? Because you want to at least bring people on board, if not ask them what to do. So it's much more messy, it's much more complicated, and creates its own challenges.
Mm-hmm. Yeah, absolutely. And it's fascinating. You mentioned the accident that caused German shutdown of nuclear power plants. I'm from Italy originally, and in 1986, when Chernobyl happened, Italy had a referendum where it decided to shut down, all of its power plants back then. So it's fascinating.
Well, I think that was the first time that the Germans decided, this is we're not continuing this in this direction. But then they changed their minds. And again, that's, these developments are all tied together. Germany has a specific anti-nuclear culture that has been written about extensively, also in part because American nuclear weapons were stationed on German soil. There were also attempts to create some kind of repositories, and when that collided with kind of the rise of the environmentalist movement, that kind of set the stage and nurtured this very strong anti-nuclear movement in Germany that has and so Chernobyl was kind of the trigger, and Fukushima sealed the deal in that regard.
Yeah, so these very rare events.
Right.
Let's see, there are several questions around disarmament. So I'm going to try to combine a few here. So question about the Russian and the Russian exit of New START treaty. How do you see the future of disarmament moving forward? If key treaties like New START are being weakened by the exit of one of the two partners.
So I'm not really an expert in nuclear disarmament. I would just offer that this is an area where I think new ideas have a really good chance of creating something new. In terms of, so since the 1970s, we have been kind of set on this one track of the non-proliferation regime that has a certain idea of, we don't increase our arsenals, we slowly lower our numbers, we verify each other, we make these treaties. But that was set up in a relatively stable geopolitical order. This is all changing now. And I just want to emphasize that in terms of disarmament, we're hearing much more today from areas of the world that have not been part of this conversation much previously, such as the African continent, such as other non-aligned countries and regions that have independently, and that goes back to that other question of who is a signatory to what treaties, where I said, it depends on which treaty you're talking about. There are treaties that have established nuclear weapons-free zones all over the world, and they go back to actually the same period as the Non-Proliferation Treaty, when regions decided we want to keep nuclear weapons out of this region. Not that in the grand scheme of things will prevent a nuclear holocaust should there ever be a full-out nuclear war, but in terms of this is possible, this is desirable, and this is what we ask for. And also, historically speaking, there have been so many initiatives demanding a nuclear freeze and nuclear disarmament. So there's a lot of educational work yet to be done or to be done again. Also, kind of pushing back against this relentless PR campaign. I showed you some pictures from the 1950s and 1960s, but we're kind of tilting back into that mode where nuclear is modern and safe and even fun and hip today, where I would caution, again, holding that tension. Yes, no doubt we have new technologies at our fingertips today. We have much more experience and all the rest. But at the same time, there are dangers that are not going to go away just because I have a spiffy social media presence about nuclear energy. And that includes nuclear weapons, and that they still exist. If you remember, a few years ago, there was this false alarm in Hawaii where people, thought this was the last moment of their lives. Yes. And they said, nuclear weapons still exist. So in that sense, I think we have a lot to reckon with. That yes, there are still a ton of these weapons around. They're not always. They're by their nature, right? They're secretive. They are knowledge about them is classified, and it's not always even clear that they still work, right? Because they're also pretty old. We haven't tested since the 1990s. So a lot of this has moved to computer simulations, but this is not in the public consciousness as much as civilian applications of nuclear energy are. And so I think the first step for me in terms of disarmament would be to just, disseminate the knowledge about where we are right now, because that seems to be extremely limited.
Great, great. And with China, as we know, increasing the number of its nuclear weapons, now we are facing potentially 3 major powers who have, large numbers, huge numbers of nuclear weapons. There are several questions in the chat about new reactor concepts, including, the thorium breeder reactors. And I'm going to just group a few of them together. So what do you see as the safeguards in non-proliferation concerns for these advanced reactor ideas that are coming forward now?
So it really depends. There are some, as I mentioned, there are some designs that are quite conventional, that are basically light water reactors of different kind. They're just miniaturized, made very small and compact, and with increased safety features, etc., such as the the new scale reactor, for example. But then there are others that either kind of pull out older design ideas, such as I think it's TerraPower that originally proposed a candlestick or a smoldering cigar type wave traveling wave reactor. That design is off the table now, but it really depends. So the issue with new designs is that the reactors that are operating today tend to operate with fuel that is enriched up to 4%, give or take. The new designs go all the way up, some of them, to the 20% threshold that is, again, pretty arbitrarily set as kind of the threshold that still counts as LEU as opposed to HEU. The issue with enriching nuclear fuel is that the technologies needed to get the uranium to that point where it contains a certain percentage of uranium-235 requires a lot of work initially, and then it kind of tapers off. So it has been argued that this initial input of labor to get to the 20% already gets, let's say, a new nation that wants to build this particular reactor that requires this particular enrichment level, gets it already 90% to the enrichment it would need for weapons grade uranium. So that's the problem in a nutshell with the enrichment level. In addition to distributing enrichment technologies in general in the first place, this is, again, often like Iran, for example, referred to the NPT and said it's in the treaty that we have a right to enrich our own uranium. How can you say we shouldn't do that? And this, as I said, these are the sensitive parts of the nuclear fuel cycle: the enrichment and the reprocessing. The reprocessing is sensitive because it it tends to separate out plutonium, which, at least in a certain isotopic configuration, can ideally be used for nuclear weapons. And again, there's differences in design. So when you, for example, when you have online refueling, you can much more flexibly adjust to what kind of isotopes you want to get out of this reactor, either to maximize the burnup or to get the weapons grade plutonium out at the perfect time. So those are that's what I was trying to convey. Those are the challenges that go beyond, can this reactor operate and produce electricity or produce medical isotopes or what have you. Those are the non-proliferation challenges that are kind of baked into a nuclear engineering problem. However, they're often blocked out and left to other people and other communities to deal with. And the same is true for the, for the nuclear weapons folks. They don't typically tend to think much about the technical aspects of the power reactors. But power reactors are also quite, as we have seen recently, can be quite flexibly adapted to, for example, produce tritium for the nuclear warheads. So those are just the things that I would like engineers to think about when they design a reactor, and that I would like, nuclear weapons experts who negotiate treaties to think about when they negotiate the details of a verification regime. There used to be these experts who had this kind of comprehensive expertise that spanned these two areas, but they're few and far in between today because we have specialized our curricula in a way that is really detrimental to this broad expertise that I think is absolutely necessary.
Yeah, absolutely. That's great. Well, that's all the time we have for today. I want to thank you so much for joining us. This was really fascinating conversation. So thank you so much. And we will see you all next week.
All right.
Bye.